Mark and James are here to amaze you with their safe cracking skills with cash, drugs, and guns.
Oh, welcome everybody to our talk, Cash, Drugs, and Guns, Why Your Safes Aren't Safe. So we're gonna start off here with a little introduction. So my name is Mark. I lead an awesome engineering team. We build embedded products. We secure embedded products. We usually work on stuff where our attackers have physical access. So I have a background in highly regulated design, industrial, aerospace, military, IoT, that kind of stuff.
And I'm James. I work with Mark, although this work is not part of our professional work. I do a lot of the same stuff, product design, sometimes cybersecurity design, sometimes cybersecurity analysis and reverse engineering, which is what I find really fun and a lot of what I contributed to this.
Like James said, the views and opinions here are not of any organization we talk about. They're not of our employer. This work was conducted independently by us. This has been our nights and weekends for the last 2 years. So, who remembers this incident with Liberty Safe, where the Liberty Safe handed over a code to the FBI responsive to a search warrant for a user's home? And so the main question to us is, how does that even work? How is that even possible that Liberty Safe is able to hand over a code to a third party that lets them open a security product that's not connected, that's installed inside their home? So we did some research. Turns out Liberty Safe uses a brand of lock called SecuRam. So SecuRam locks are UL certified high security electronic locks. And of course, the first stop in any reverse engineering, we go to eBay, we buy one. So we bought a Liberty Safe toplet. Turns out these are actually OEM'd by SecuRam. And so we want to take a little side note, talk about the terminology we use. So we call the outside part of the safe the keypad. This is where you type in the codes. It's got a little screen, shows you some nice information. That's connected via cable to the latch. The latch is the inside part of the safe. That's the part that keeps you from turning the handle to open the safe when you haven't entered the right code.
So we've got a SecuRam toplet, latch, and keypad, and we set about reverse engineering it so we could figure out how this stuff worked. And the SafeLogic series, which includes the toplet, all the smarts are in the latch inside the safe. The keypad does have a microcontroller, but the only function it has is turning an LED on and off. So we're really just interested in what's inside the latch. And the hardware is pretty simple. It's just a microcontroller and a little motor driver that opens and closes the latch, or allows it to open and close. So what we really need to reverse engineer is the firmware on that microcontroller. And it's kind of a weird old processor, this Renesas 78K0S KX1 series. So it doesn't actually have a mechanism to read out the firmware. That they didn't disable it, it's just not part of that microcontroller's boot ROM. But we figured out a way to get it to spill its guts and read out all the data in the flash. We gave a talk on that at Hardware.io last year if you want to know more about that, but it's a new exploit we came up with against that part. So with the firmware out, we reverse engineered it. This was a mostly manual process. It's a bit of a weirder, older architecture. There was no support in Ghidra, no support in IDA, no support in any reverse engineering tools that I could find. So we wrote our own disassembler, which was pretty fun. And from the disassembly, we manually translated that back into a sort of pseudo-C. We worked through all the bytecode in the device so that we weren't missing anything. And we figured out, at a high level, how does everything work? So this lets us answer the question, are there any super secret backdoor codes? Is that how Liberty Safe is able to do this thing? No, there's not. In the SafeLogic, there's two codes, manager code and the user code. Both of these unlock the safe. The manager code is a little special because it can disable or change the user code, but those are the only ways programmed in that let you open the lock. There's no secret backdoor in the code. But as an end user, you might not necessarily know about the manager code. So Liberty Safe, as an example, when we bought our locks from Liberty Safe, we got two sets of documentation. One intended for the person installing the lock and one intended for the end user. The end user manual does not say anything about the manager code. It only describes one code, and that's the user code. So in Liberty Safe's practice, which is not necessarily unique to Liberty Safe, they set the manager code, and they keep a record of that with the serial number of the safe. The well-intentioned version of this is that they can use that to help you out if you get locked out of your safe. Perhaps they handed out responsive to a warrant. They did change their policy around this. So responsive to, the kind of controversy that emerged, I think they're more strict about when they'll give that out. You can request that they delete it, and you can also reset it yourself. There's just a little pinhole in the lock that lets you clear both those codes back to default. But this isn't a problem with the lock. The lock is doing exactly what it says it does. Both those codes are in the operating manuals from SecuRam. They're easily found online. There's no secret backdoor here. This is really just a management practice employed by Liberty Safe, for example, but it's also a management practice recommended by SecuRam in certain documents that you get with the locks, like the printed manual that comes with some of their locks, intended for an audience of like safe integrators or OEMs. So this management practice is just that. It's not indicative of any technical backdoor or failure in the lock itself. And really, after looking through everything, what we realized is that these locks are fine. We didn't find any clear exploitable security vulnerabilities in the lock at all. The only thing we found, which is not a best practice, they use a non-constant time compare on the unlock code when they're comparing that to what you entered. But we weren't able to exploit this to actually get an advantage in opening the lock. And even if we could, there's like a 5-minute timeout every 3 wrong codes. It would be very difficult to exploit this in the field anyways. So we think it's pretty secure. In safe logic mode, in analog mode. Where is he? Get up here.
All right, so talking about analog mode, turns out there's also a digital mode. In analog mode, the way the lock works, when you hit a keypad button, it transmits that as an analog voltage down to the lock. But of course, there's actually a digital code. For the eagle-eyed among you, I know you're all out there, the struct that James showed had an enum that said lock type. It said analog lock type. Turns out there's a digital lock type with a whole bunch more interesting code in the latch. So it turns out SecuRam actually has a whole digital line of locks. These are called the ProLogic and ScanLogic series of locks. So we've dug into the ProLogic series first. So we looked at the ProLogic L02 as kind of our main example. So this is the most popular lock in their digital series of locks. This is another UL certified high security electronic lock. So, of course, we expanded the scope. Now we've kind of gotten this curse. We have dozens and dozens of locks. We have debug tools. We have interfaces. We have cables. It's gotten way out of hand. I have too many boxes of stuff in my office now. So some interesting facts that we got. When you reset the latch on this lock, we actually found it doesn't reset the codes that you use to open the safe. If you recall, in the safe logic, when you reset the latch, it does reset all the codes. We found this really interesting. It also has this recovery mode. This lets you call the factory, you get a magic code, and this code does reset all the codes on the lock. And of course, we read the manual, and it talks all about the encryption and the security in these locks. So, first step, we got to figure out what's inside this lock. So it turns out it's a Renesas RL78G13 lock. Luckily, this was a processor in the PS4. So the gamer hackers, they already took care of it for us. No need to exploit anything, no need to make any new research. Failoverflow has a really nice blog post that talks about the work that they did. And of course, the more widely used this processor is, the bigger the attack surface. And the PS4 is a huge attack surface for locks.
So with that in mind, we're going to look at the code now on the ProLogic keypad, and we've actually got to get it out first. Like Mark said, failoverflow is going to make that pretty easy for us. But so on this processor, there's a combined flash programming and debug pin, which is called the tool pin. It's basically a bidirectional UART. And the flash programming mode on that pin doesn't have any code, doesn't have any command that lets you read out the flash memory. It has a debug mode that has some commands like write to RAM and execute from RAM. So we can just upload a little piece of code that takes over the tool pin and sends out every byte of memory over the tool pin as a UART, including all the firmware, all the data, all the RAM, everything. So flash programming mode is publicly documented by Renesas. It's very cleanly documented. It's pretty easy to use. Debugging mode is, they tell you all about what it is and what it does, but the actual line protocol is not documented by Renesas. Fortunately, it is documented by failoverflow. So we were able to leverage their work to a huge extent, and they actually even had a reference implementation of this protocol. But there's still a little bit of work we have to do because there's a couple security measures that we have to bypass. Basically, two things. You can disable debugging on the processor, and you can set a password that you have to supply the correct value of in order to access debugging. So failoverflow documented that you can glitch patch past these and had some good info about how, but not an actual reference implementation. So we've got to set that up ourselves and figure out the glitch parameters in order to bypass that. The first step of the first step is, of course, actually getting connected to the pins. That's pretty easy on this lock because it's also the programming port, so SecuRam has brought it out as this nice labeled header here. You can also see it through the battery door. We're going to take advantage of that later. So aside from those 4 pins, the only thing we've got to do is set up for some voltage glitching. So we take off the core voltage regulator capacitor and we replace it with a little MOSFET that we're going to control so that we can get the processor into a weird state and make it not do some of these security checks correctly. So we're set up, we're ready to start figuring out our glitch parameters. It's all running on a Raspberry Pi Pico. We re-implemented this stuff and, you know, I think I'm pretty good at this stuff, but I don't expect a new to me glitch on a processor I don't really know much about the internals of. I don't have any idea what the glitch parameters are supposed to be. I don't expect it to work on the first try, but it did. And it turns out the reason that it did is because they didn't disable debugging. So we didn't have to glitch past that. That's easy, that's nice. Makes my life easier. But we still need to figure out the unlock code, or Renaissance calls it the debugging ID. That's a 10-byte code that we have to figure out. And failoverflow also documented how you can glitch past this and kind of dump it anyways, and once you dump it, then you know it, so that makes it easy. But, you know, I mean, I like to try some of the easy things first. Let's try a few basic passcodes like all zeros. It's all zeros. So we actually didn't have to glitch past anything. We didn't violate any of the security guarantees of this microcontroller. We didn't exploit anything. We just read the code out for the debug port. So we've got it. We're going to bring it into Ghidra, and we're going to start looking at it. Thank you to XYZZ on GitHub for their Ghidra RL78 plugin. I'm pretty good at Ghidra, still haven't quite figured out how to implement a new architecture, so this was a huge help. It does struggle a bit. It's got a weird 1620-bit address space on this part. It's 20 bits, but sometimes you only know 16. Makes it very nice to reverse engineer. Anyways, we fixed it up, we worked through it. We didn't look at every single byte of code, but we looked at everything that, you know, we found everything that's in the manual. We found how that stuff gets accessed. We checked to see if there was anything else you could access that wasn't in the manual. Those are that's the level of checking we did with this. And we at least got to the level of understanding how everything critical works. How does it check unlock codes? How does the recovery process work? How does it talk to the latch inside of the safe? And when we fully understood that, we realized there were some interesting design decisions in this lock. So one kind of paradigm we have to establish is, where do the codes go? Do they go inside the safe or outside the safe? Because outside the safe is also where the people who you don't want to be inside of the safe also are. And inside the safe is protected by steel and concrete and whatever else goes into a safe. I don't know, I'm not a safe engineer, but it should be at least as secure, you know, as the valuables you're trying to protect, or the guns or whatever. So what do you think they did? In the case of this product that we analyzed from SecuRam, what they actually did is they put the codes in the keypad outside of the safe. So if we read out the data flash the same way that we did reading out the firmware and everything, and the data flash is, as the name implies, it's flash used for storing data. Yeah. The supercode is just right there. It does look a little funny though.
So for those of you who remember, this OEM, we talked all about the encryption. So it turns out that this supercode is stored encrypted. You might notice it's really long for just storing a 6 or 8 digit code. And the supercode on this processor, this is kind of like the root password. Lets you bypass things like time delay, lets you manage and change the codes of all the users. It lets you manage all the settings on the lock. It's encrypted with a protocol called XXTEA with a 128-bit long key. This protocol, this key length, is considered secure against things like brute forcing, GPUs, that kind of stuff. There's no reasonable sized GPU cluster you could use to brute force this. So how do we actually decode this? If we can't brute force it, we can't do that. Luckily, SecuRam made a great decision for us. They put it right in the flash, right next to the supercode. Luckily, all we got to do, read it out, decrypt the supercode, add the 96 bits of static key bits that don't change, and then we can just decrypt the codes. So there's another lock that's part of their digital lineup. So we looked at the Scan Logic Basic. Unfortunately, this one is not as advanced as the LO2. It doesn't feature any encryption. It just stored it right in the flash. You can just read it right out, plain text. So now let's talk about how do we actually attack this processor. So we made this great tool. It started out, I designed this beautiful board. It was the right shape. And as we started working on it, we needed to bend it a little bit. We needed to run some wires because we broke it. We got to glue it in place. So now it's acquired a little bit more of a hackery look. So all we got to do, we take it. It reaches way up in there, right up to that debug port, connects right in. And we go through this long, complicated process, this complicated exploit. First thing, we enter debug mode, not disabled, enter the debug key, all zeros. Then we inject a blob of code, we patch that debug RAM, and then we dump all the codes in 0.8 seconds. We actually are to optimize it a little better. It's slightly better than this now. So this is an exploit we called Code Snatch. And so now James is going to give us a short demo on the safe here. All right, so first we got to take out the battery door and then go and put this tool in. It's a little bit awkward to get in there. We're not mechanical engineers, we're electrical and firmware engineers. But after we get it in, he's going to turn it on and it's going to read out the code. So you can see the code here is 001337. So now we got to put the battery back in, wait for our safe lock to boot up, which takes a surprisingly long amount of time. Keep going, keep waiting here. There we go. Now we're all booted. Now we can try out that code, see if it was the right code for us. And boom, there we go. Of course, with the GSA container, we always got to indicate what state it's in. So we got to leave it in the open state at all times for this safe. All right, so who actually uses these things? I mean, anybody serious, right? So it turns out they're used by these OEMs for consumer safes. SecuRam in a 2021 interview claims that they have 70% of the smart lock system market in the US and that they sold to approximately 3 million customers in North America. We're not sure what the split is between the vulnerable and non-vulnerable locks, but as far as we can tell, they have high penetration in the market. So they're used by companies like Liberty Safe, Fort Knox, Rhino Metals, Fire King, ProSteel, Tracker Safe, High Noble, Sun Noble, those kinds of companies. We didn't actually buy locks from all these companies. What we did is our exploits work on locks manufactured between May 2014 and March 2025. So we looked to see if these vendors sold at least one of the vulnerable models during the overlapping with those manufacturing dates. So these companies sell safes that are designed to protect things like firearms and personal documents, things like that. So besides firearms, what are they used for? Anything actually serious? So we took a look. Turns out these are big in pharmaceutical safes. Safes used to store and protect narcotics for manufacturers, distributors, pharmacies, hospitals. The L02 appears to be the safe lock of choice for pharmaceutical locks, especially in the low-end market. It's the cheapest safe lock that actually supports the required features like time delay and multiple access users. So it's the default choice, as far as we can tell, on Xenox pharmaceutical safes and NarcSafe pharmaceutical safes. NarcSafe, luckily, they list a couple of their users. They're used by some of the largest pharmacies in Canada, like PharmaChoice, which has over 800 locations, and other people like the government of Canada is listed as a user for them. So we wanted to go see, are these actually out in the world? So on the right hand here, you can see a screenshot from a news story a couple of years ago where CVS updated their whole fleet of locks to add time delay as part of the opioid epidemic. And on the left here, it's actually one of my favorite pictures of CVS locks in the wild. You can see there's a Pro Logic right on the front here. Turns out, in the background, 2 more bonus Pro Logics in this image as well. So as far as we can tell, all the coverage we showed for CVS, they all use these L02 locks at that time. So they're also using cash drop safes. So we found there's this brand, CSS. They are a managed safe provider, later acquired by Xenox. So here's a picture of a cash drop safe in Subway. Here's one in Papa Murphy's. Here's one at Taco Del Mar. Here's one at T-Mobile. It was quite easy to find a number of pictures of these being installed in places. So what can we actually do about this? So as far as we can tell, there are no mitigations for code snatch that don't involve updating the firmware on both the latch and the keypad to move those codes from the outside to the inside of the safe. When we went back and forth with SecuRam, they sent us a safe with a lock and a latch installed with updated firmware. It looks like it moved the codes from the inside to the outside. We never actually got a code for that safe. We never opened it to see it was functional. We weren't really able to tell if the whole system worked. But a month ago, we bought a lock from distribution to see if anything had been updated. And that lock was made in March of this year, and that lock did not mitigate the error where the codes are in the keypad. They set the debug code on this to something that's not all zeros. This doesn't really mitigate it. We just added the new value to our tool. So we can actually do a field firmware update on these parts. The tool we made here, it connects to the debug port, it speaks the debug protocol. You could absolutely use this or a low-cost tool like it to update both the latch and the keypad for these devices. We didn't actually implement this functionality because we didn't go rewrite their firmware for them, but it's something that you absolutely could do.
So that requires specialized hardware that we made, that cool little tool, and it only works on a subset of their locks, as we'll explain in a minute. So is there an easier and more effective way in? Is there something different we can do? Well, remember the lock recovery feature. So to quote the manual, system recovery is used to delete all the codes on the Pro Logic or Scan Logic and set the entry pad, keypad, and its linked lock latch back to a factory default state. And this kind of works by, you have to be a locksmith to do this with them, but you call them, they do something on their end, and that lets you reset the safe. So what does that process actually look like? You get into the menu, and you can get into some of the menus even if you don't know the codes. This is one of them. You try to recover the system, you put in your code, that's 999999 by default. It's a special code used for accessing this mode. It shows a recovery challenge on the screen, which is what you're seeing there. You call SecuRam as a locksmith, tell them what it says, they give you another code to type in, and all the codes on the lock are reset, including the super code. So now you know that, now you own the lock, you can change any settings, you can do whatever you want. So how does it actually work from a technical perspective? We feed a few pieces of data into an algorithm, and we get the response code. So the data that goes in includes the recovery challenge, which is a random number, it's part of what was shown on the screen, the recovery code, which you had to know to access this mode, the encryption code, which is a different special code on the lock. SecuRam doesn't mention it as much in the context of the recovery procedure. It is part of the computation. You can also change that. And the other things that go in are either constants or not secret, like information about the configuration of the lock. That all goes into something to make the response code that you have to type in. And that something is also XXTEA. And what's important about that is a symmetric cipher. So there is no secret piece of data in this operation that isn't in the lock. There's no secret that only SecuRam has. And there's also no hardware security module on this lock that they could use to hide part of that computation or hide part of the secrets. So it's all in the firmware. And when we reverse engineer that, we learn exactly how to do this computation and produce the correct response code. So Mark is going to show you that now we're the OEM. We can do this. And where is that? Oh, yep. Here we are. Oh, whole thing, please. So he's going to start by putting the lock into recovery mode, typing in that default code of all 9s. And that's going to show him the challenge code on the screen there. He's going to type that into this little web app we made. I mean, it's just a single page thing running some JavaScript. And it's going to run the computation that we pulled out of the firmware. And it's going to produce that response code. He's going to type it in. Two. User code verified. And now it's saying it's going to reset everything to the default. If you'd like, we would like. So now everything is back to normal. Supercode 111111. You can do whatever you want. And Mark is going to show you that by typing in 111111. One more one, please. And we're in again. So yeah, and we gotta make sure we keep track of whether it's open or not. Where are my slides? There we go. So what about the recovery and encryption code, right? So we did that with those at the default. So is this really a thing? Do people just leave those at default? Well, we've got 2 data points from SecuRam on whether or not you should change these codes. And how to change them is perfectly easy to find. These are in all the manuals. You can look up how to change it. But should you change it? We got 2 data points. One is a webinar from SecuRam, which is still on their YouTube channel today. And this is a screenshot from that. Usually never changed. Quote, "The encryption key is rarely changed, at least in the North American market. No one ever changes this key. You can change it, but most people leave it as default, and that's fine. The recovery code is also usually never changed because there is no security risk in leaving it as 6 9s as we saw previously." So that's an interesting statement, but fair enough. This is a matter of opinion, maybe. The other data point is more positive. In some of the printed manuals that ship with some of their locks, and this is the same manual that recommended keeping the database of unlocked codes for OEMs, they do recommend changing the recovery and encryption codes, which is a good recommendation. We can't find this online. So whether you as an end user will be exposed to this recommendation, it's hard to say. But that's the recommendation we would make. Change your recovery code, change your encryption code. That's going to be the main mitigation for end users. You can't change the recovery code without doing the same have a locksmith call into SecuRam thing, but you can change the encryption code yourself. You can also disable recovery. I don't remember how that works, but it's possible. Beyond that, I think what we would want to see is an asymmetric cryptographic protocol used for this process so that at least there's some secret that is not in the lock that's needed to produce the correct response. Beyond that, it's up to you, whether you want this feature in there or not. They do provide a method to disable it, so. What does this actually work on? Reset Heist that we just showed you with the little phone thing, that works on every lock that we tested that has that feature. So we didn't test every lock that they make, but we tested a lot of them. ScanLogic Basic, for instance, doesn't have this recovery feature, so obviously it doesn't work on that. But locks made from May 2014 to March 2025 were all vulnerable to this insofar as they use the same algorithm and the same default values. That includes several locks that we purchased secondhand from eBay with the caveat that the seller did not know any of the codes and could not help us open it. Even on those locks, they were left at their default values. Code Snatch, with the little tool that reads out the codes, is a bit more specific in what it works on. It works on LO1s and LO2s manufactured starting sometime between 2019 and 2022. They switched over to a new processor, and we don't have any exploits against the old processor today. It also works on that ScanLogic Basic, not sure exactly when that model was introduced, but it does not work on some of their older ProLogic locks. So obviously we have to tell SecuRam about this. This is kind of important. I'm just gonna walk you through the whole timeline. September of 2023, we read the article from the New York Times about this Liberty Safe stuff, and we say, huh. In December, we start actually looking into this. How did they manage that? And this is mostly Toplet, SafeLogic. We expand that to ProLogic pretty quickly. In March, we let SecuRam know that we were looking into it. We didn't have any vulnerabilities to report at that time. But in April, we provided them with a detailed technical disclosure explaining all the same exploits that we showed you in this presentation today. In May, their response to that was, quote, "We will refer this matter to our counsel for trade libel if you choose the route of public announcement or disclosure." Also, quote, "The attack method you have indicated is not new." And in the context of this is they're talking about certain tools that are intended to only be sold to locksmiths, which have the capability of opening some of their locks as well as some other brands of locks, according to the vendors of those tools. So this kind of put a damper on our activities, but in November of 2024, we were feeling like this really is important. We really have to talk about this. We reached out again saying, we're going to present sooner or later, and got pretty much the same response. The EFF in December, thank you very much to the EFF, reached out on our behalf to say, yeah, give them a round of applause. They reached out on our behalf to say basically the same thing and also offered to include a statement from SecuRam in any presentation we might make. We did not get a statement at that time. June, accepted here, woo! And we requested again a statement from them, didn't get one at that time. Just last month, July, for the first time, we heard from their lawyers instead of just from their management. This was actually somewhat more productive, but we still didn't get a statement from them at that time or at all. They did not provide a statement to us by the time of this talk. 15 months after the initial technical disclosure, almost 2 years we've been working on this. It's DEF CON. We're telling you all about it. So, yeah, thank you. A couple interesting quotes from our communications with them. "We don't believe it is appropriate for you to communicate to our customers of any concern. Your disclosure to our customers would interfere with our relationship with the customers." And you know what? We said, okay, it's your product, it's your customers, you've got a moral right to handle this with them how you want. We have not reached out to any of their customers. We have not reached out to the safe vendors involved. We did send an initial email to Liberty at the very beginning, but we never heard back and we never chased that down. Other quotes. "We object to your sharing or disclosure of your findings, even at a conference, as such disclosure as you presented would be misleading and damaging to SecuRam's goodwill and reputation." So, well, hey, no comment. But we wanted to give this talk at DEF CON last year, and we didn't. Because of statements like this, we decided not to give this talk last year. This does mean they had a full extra year to address this in a manner of their choosing. We haven't received a statement from them, so we don't know what their plans are to mitigate these issues, if they plan to mitigate them. They did send us that one lock that was maybe moving the codes inside the safe. It's not in the wild, as Mark mentioned. And really the only other thing I can tell you about this is what Mark said earlier, which is that we purchased a lock last month, made in March of this year, made 11 months after our technical disclosure. The codes are still in the keypad. It's still fundamentally vulnerable to both of these attacks. That's all we know. If you're affected by these issues, you should reach out to SecuRam.
All right. So I want to talk a little bit about the prior art. So we learned about these tools from them, and after they mentioned it, we took a deep dive into these two tools, the little black box and the Phoenix tool. These are locksmith-only tools that allow locksmiths to do things like variously resetting codes, opening safes without codes, getting the codes out of locks, stuff like that. And so these tools work on a wide variety of safe brands, including SecuRam, Lagarde, Sergeant Greenleaf, AMSEC, Dormkaba, the major brands inside these kinds of high-security electronic locks. And what really blew us away is that these are safe locks with known exploited vulnerabilities. They make these awesome tools to exploit them for you. It blows me away that people are still using these locks, that these models haven't been discontinued. I mean, would you use software with known exploited vulnerabilities in it? So these tools, they actually don't open ProLogic locks, and they only open ProLogic locks before 2016. Luckily, we're able to help fill the gap. So sometime in 2021, 2022, maybe earlier than that, they switched over to this new processor, and that's what our attacks work on. So in 2016, Somerset Recon demonstrated a Bluetooth sniffing attack against the ProLogic B01. So this is a discontinued Bluetooth model of lock. I don't know if I really want Bluetooth in my safe locks. Separately, they demonstrated unlock capability against a latch unit at that time as well. And then Deviant also had a great talk on locksmith tools, including the little black box and the Phoenix tool at PancakeCon in 2024, which has some great info in it as well. So we have some opinions, some opining that we want to do here. The first one is, does it really matter? Is this a legitimate threat to security? One of the things that we heard is that, this attack method that we used is more effort than people are willing to put in. This is, we used advanced techniques. We were prepared and willing to do glitching against these locks. When we investigated other models, we found novel, unknown exploits to microcontrollers. We did deep reverse engineering, new processors, new disassembling tools, lots of analysis. Is this something that that threat actors can actually do? Is this something that people are willing to do? And we would say the answer is absolutely yes. Organized crime rings absolutely have the capabilities to execute attacks like this and make tools like the one that we demonstrated. They already make credit card skimmers, which can be incredibly sophisticated pieces of technology. They also make and sell tools that you can connect to the CAN buses on cars to unlock and steal them. Those kinds of attacks, those kinds of analyses, those kinds of tools far exceed the capabilities we had to bring to bear to analyze these locks. And the other group of people is nation-state threat actors, way within their capabilities to do this analysis, to do this reverse engineering, to do these attacks. It's absolutely within the capability of state police-like organizations, FBI and others, to do this reverse engineering, build these kinds of tools. And these vulnerabilities, these aren't just theoretical, we glitch it for 20 hours, something's weird. These are vulnerabilities that let you open in minutes, as we demonstrated here. These are things that are very real, very absolutely possible for people to use. And attacks like Code Snatch leave almost or zero trace. You're able to get out these codes, then you own the keys to the kingdom on these locks. So when thinking about the threat modeling for safes have only one function: keep people with physical access to the outside from getting physical access to the inside. And to that effect, there is no way in which you can put safe codes on the outside of the lock without reducing the security of the system. Safe codes are only 6 to 8 digits in almost all electronic locks. They are incredibly short by modern standards for passwords. There's no hashing scheme, there's no cryptographic scheme that can protect these from you. If everybody today, your phone could in seconds crack a SHA-1 hash of a safe code, and even if you did something like use bcrypt with a work function so high, it took 20 hours for the processor in this keypad to check if it was right, it would take you a fraction of an hour on a desktop GPU to brute force that code. So, really the thing to ask in this point is, what went wrong? Where was the biggest failure in this chain that caused this to happen? The easiest person to point to is SecuRam. We can say they implemented these locks insecurely. They didn't consider the threat models. They didn't set the debug codes. They didn't use the features that they should have to protect the locks. And I think you might imagine, gosh, what about the safe OEMs? They're the ones picking these locks. They're the ones choosing which ones to use. Shouldn't they have done something like evaluated them on their own, done analysis, investigated what's going on? Are these really secure? And I think if you asked them, they would tell you that these were certified by UL. These are certified high security electronic locks. This is a certification that is baked into US code for DEA safes and other applications. And so I would say it's not UL's fault here. They correctly applied a standard that is wildly out of date for modern product security. The product security for physical products lags significantly behind the state of the art for product security that we understand today. You should be able to trust the certifications. They are there to set the minimum standard for manufacturers to meet, and they are there for the users to understand what is and isn't a high enough quality product for their application. So let's go back to this list of locks here, the little black box and the Phoenix tool. There's almost 50 unique models on here. How many of you guys think less than half of these locks are UL high security certified locks? Raise your hands. Oh, nobody. Yep, you're all right. Almost all of these are UL certified high security locks. Almost every single one on this list of known exploited locks meets that standard for high security locks. The only ones that aren't highlighted here are the ones where I couldn't actually find the certificate showing that model was certified. So what really needs to happen is that safe lock products and locks, they need to require a secure product development framework. We can't have security through obscurity for locks and physical access. We need threat modeling, risk assessments, functional flow descriptions, independent white box, black box testing. We need FIPS and common criteria type evaluation and certification of cryptography and side channel resistance for these devices who have no other function than physical security. Some other industries who do things besides physical security have done an amazing job. The FDA has one of the most stringent cybersecurity regimes in the world for medical devices. They have really raised the bar, requiring almost all of these things for medical devices, as well as the National Highway and Transportation Safety Administration has significantly raised the bar for vehicle cybersecurity. And the UL and the lock industry need to bring the standards that are codified by statute in line with modern standards. We can't be questioning whether or not these certifications mean anything. So another thing, I want to talk a little bit about Chinese government backdoors. Seen lots of hype in the media about backdoors by governments that have been put into devices and things like that. We found no evidence of any such feature in the locks we evaluated, and we definitely looked. When we say backdoor, we're talking about manuals that are not declared in the feature, features that are not declared in the manual. And so don't believe the hype. Bad design is not the same thing as a government backdoor. I certainly hope if people are designing government backdoors, they do a lot better job than they did here. So one more thing, I want to have a huge shout out to the Electronic Frontier Foundation and the Coders Right Project. They are the reason we are here today presenting to you guys. They represented us, they helped us understand everything as we went through, and we are grateful to them for all of the support that they provided to us throughout our whole experience. Thank you guys so much. I think we have a few minutes for questions. All right, we'll take questions outside. Happy to chat with you guys. Thank you.